In 1825, Marc Brunel proposed building a tunnel beneath the River Thames, not a shallow culvert or a drained trench, but a true tunnel bored through waterlogged clay 40 feet below the riverbed. The brick-lined walls he specified were 3 feet thick. Engineering committees called it impossible. Insurance companies refused coverage. Investors demanded he reduce the wall thickness to save costs. Brunel refused. Today, 1980 years later, those same walls cacker the London Overground beneath the Thames. The skeptics are forgotten. Brunel's tunnel endures. The Thames at Rotherhithe was 200 feet wide, 50 feet deep at high tide. Beneath the riverbed lay Thames clay, dense, waterlogged, unstable. Previous attempts to tunnel under rivers had ended in disaster. In 1807, engineers tried to dig beneath the Thames at Gravesend. The river broke through. 8 workers drowned. The project was abandoned. In 1824, another attempt at Rotherhithe flooded within weeks. The conventional wisdom was clear. Tunneling under a tidal river could not be done. Marc Brunel was not a conventional engineer. Born in France in 1769, he had dead the Revolution, worked in America, settled in England. He held patents on machinery for making ships' blocks, sawmills, and boots. He understood manufacturing, mechanics, and innovation. When the Thames Tunnel Company formed in 1824, they needed someone willing to attempt the impossible. Brunel was their only choice. His solution was radical. Instead of excavating the tunnel in one large diameter, he would use a rectangular iron shield, essentially a moving framework that protected workers as they excavated small sections of the tunnel face. The shield would advance by jacks, pushing forward into the clay. Behind it, bricklayers would line the tunnel walls immediately, preventing collapse before the shield moved ahead. This had never been attempted on such a scale. The tunneling shield was 38 feet wide, 22 feet high, divided into 12 vertical frames. Each frame contained 3 working cells, one above another, 36 cells total. A miner occupied each cell, excavating the clay face in front of him. The cells were just large enough for a man to work, 3 feet wide, 6 feet high. The miner removed clay by hand, placing it in buckets hauled away behind him. As he excavated, he removed horizontal boards, supporting the clay face, working from top to bottom. When all boards in his section were removed and the clay excavated to the required depth, hydraulic jacks pushed the entire shield forward by inches. Behind the shield, bricklayers worked in shifts. The tunnel was designed as 2 parallel arched passages separated by a central wall. Each passage was 14 feet wide, 16 feet high. The walls were specified as 3 feet thick, not because structural calculations required it, but because Brunel refused to trust the Thames clay to remain stable. He had studied the 1807 collapse. He knew the river could break through. Extra thickness was insurance against catastrophic failure. The bricks themselves were specially made. Standard London stock bricks were too porous for underwater use. Brunel demanded engineering bricks fired at high temperature for maximum density. Each brick was tested for water absorption. Rejected batches were common. The mortar specification was equally demanding. Roman cement mixed with sand, capable of setting in damp conditions. This was expensive mortar, costing twice as much as standard lime mortar. It remains intact today. Work began in February 1825 with the construction of a vertical shaft at Rotherhithe, 50 feet in diameter, 63 feet deep, sunk through clay to the level where horizontal tunneling would begin. The shaft was built using cast iron rings, each section lowered and bolted together as excavation progressed. Workers dug by hand, hauling clay to the surface in buckets. Progress was measured in feet per week. By November 1825, the shaft was complete. The tunneling shield was assembled at the bottom of the shaft. It weighed 120 tons. Cast iron frames, wrought iron jacks, timber bracing. Lowering it, section by section, required careful engineering. Once assembled, it filled the chamber at the shaft bottom. Marc Brunel's son, Isambard Kingdom Brunel, aged 19, was appointed resident engineer. He would supervise day-to-day operations underground. Tunneling commenced in November 1825. The shield advanced by inches per day. Miners worked in the cells, excavating clay in near-complete darkness. Candles provided the only light, flame flickering, shadows dancing, air thick with moisture. The clay was dense, sticky, difficult to excavate. Tools had to be cleaned constantly. Progress slowed in winter as cold temperatures made the clay harder. By March 1826, the tunnel had advanced 40 feet. In May 1826, the Thames broke through. A miner removing a board from the tunnel face encountered not clay, but liquid mud. Before he could react, water poured through the opening. The shield flooded within minutes. Workers scrambled toward the shaft, wading through rising water. The tunnel filled to the ceiling. One man drowned. The others escaped by climbing the shaft ladder. The river had won temporarily. Marc Brunel surveyed the damage. The tunnel was full of Thames water. The clay face had collapsed. The shield was buried in mud. Most engineers would have abandoned the project. Brunel ordered the breach sealed from above. Divers descended into the Thames, located the hole in the riverbed, and filled it with bags of clay and gravel. Pumps were installed in the shaft. The tunnel was drained over 6 weeks. In August 1826, work resumed. The shield had survived intact. The brick lining behind it showed no damage. The 3-foot walls had held. Critics, who had called the thickness excessive, now fell silent. The tunnel advanced again, more cautiously. Miners probed ahead with iron rods. Before removing boards, testing for soft ground, progress slowed, but remained steady. By 1827, the tunnel had advanced 150 feet from the Rotherhithe shaft. Work continued for 2 more years under brutal conditions. The tunnel was perpetually damp. Water seeped through the clay constantly. Pumps ran 24 hours per day. Miners worked in standing water, clothes soaked, boots filled. Respiratory diseases spread. Cholera outbreaks killed workers. Exact casualty figures were not recorded, but contemporary accounts mentioned dozens of deaths from disease, accidents, and drowning. Funding became critical. The Thames Tunnel Company had underestimated costs. Construction was taking twice as long as projected. Investors grew impatient. In 1828, the company ran out of money. Work stopped in March. The shield was left in place. The tunnel sealed at the Rotherhithe shaft. Marc Brunel lobbied Parliament for funding. His requests were denied. The tunnel remained abandoned for 7 years. In 1835, the government finally allocated funding, partial support, enough to resume work, but not complete the tunnel. Operations restarted in August 1835. The shield was still functional. The brick lining remained sound. Tunneling resumed. Progress was faster than before. Experience had taught the crew how to work efficiently. By January 1838, the tunnel had advanced 600 feet. The Wapping shaft was under construction on the north bank. Completion seemed achievable. On January 12, 1838, the Thames broke through again. This time, the flood was catastrophic. A section of riverbed collapsed directly above the tunnel. Water poured through a hole 15 feet wide. The shield chamber filled in seconds. Isambard Brunel was underground when it happened. He barely escaped, swimming through darkness toward the shaft. 6 workers drowned. The tunnel filled completely. The damage was severe. The shield was buried under tons of silt. The tunnel was full of debris. Marc Brunel, now 70 years old, considered abandonment. Isambard, recovering from near drowning, insisted on continuing. Divers sealed the riverbed breach with iron plates and sandbags. The tunnel was pumped dry over 4 months. In June 1838, work resumed for the 3rd time. The final push took 5 more years. Tunneling was slower, more cautious. Every foot was tested before excavation. Water ingress remained constant, but manageable. The brick lining continued behind the shield, 3-foot walls, Roman cement mortar, engineering bricks tested for porosity. Inspectors examined every joint. The work was methodical, exhausting, expensive. In August 1841, the shield broke through into the Wapping shaft. The tunnel was complete, 1,200 feet long, connecting Rotherhithe and Wapping beneath the Thames. It had taken 16 years. It had cost lives, bankrupted investors, defied engineering consensus. But it worked. The tunnel opened to pedestrians on March 25, 1843. 50,000 people walked through it on the first day. The public was fascinated. Descending spiral staircases into the Rotherhithe shaft, walking beneath the river, emerging at Wapping. It was the world's first underwater tunnel. Engineers from across Europe visited to study the construction methods. Marc Brunel was knighted. Isambard became the most celebrated engineer of the Victorian era. The tunnel never achieved its intended purpose. Plans called for it to carry horse-drawn carriages on spiral ramps. The ramps were never built. The company had no funds remaining. The tunnel operated as a pedestrian crossing, only it became a tourist attraction, a curiosity, a minor commercial failure. But structurally, it was flawless. In 1865, the East London Railway purchased the tunnel. They laid tracks, installed ventilation, and began running steam trains through it. The 3-foot brick walls, designed to resist water pressure, now absorbed vibration and soot from locomotives. The structure handled the load without complaint. The mortar joints remained sound. The bricks showed no deterioration. By 1900, the tunnel carried electric trains. By 1950, diesel. By 2000, modern electric multiple units. Today, it carries the London Overground trains. Every few minutes, thousands of passengers daily. The tunnel, built in 1843, remains in constant use, handling loads Marc Brunel never imagined, but walls he built thick enough to accommodate. The Thames Tunnel proved that underwater tunneling was possible. Every subsequent subaqueous tunnel, the Severn Tunnel, the Mersey Tunnel, the Channel Tunnel, owes a conceptual debt to Marc Brunel's shield design. Modern tunnel boring machines are direct descendants of his 1825 invention. The 3-foot brick walls were not wasteful excess. They were engineering insurance that paid dividends for 2 centuries. Marc Brunel died in 1849, 6 years after the tunnel opened. He never saw it carry trains. He never knew it would still function 98 years later, but he built it knowing it needed to last, not for his generation, but for every generation after. The 3 feet of brick were not optimized for 1843, they were optimized for indefinite survival. Modern tunnels are engineered to minimum safety standards. Materials are optimized for cost. Replacement is anticipated within 75 to 100 years. Brunel's tunnel, built with hand-excavated clay, candlelight, and Roman cement, has operated for 81 years with minimal maintenance. The irony is not lost on engineers who study it. Better materials do not guarantee longer life. Intent does. The Thames Tunnel stands today, carrying the London Overground beneath the river, brick walls intact, mortar joints sound, structure stable. It is not a museum piece. It is active infrastructure, doing exactly what it was designed to do, carrying loads far heavier than Marc Brunel anticipated, but walls he built thick enough to handle. Victorian engineers are sometimes accused of overbuilding, wasting resources on unnecessary strength. The Thames Tunnel suggests a different interpretation. They were not overbuilding, they were building Ricola. They simply refused to assume the future would be kind, and 98 years of history proved them right.